We use the words variability and spread somewhat interchangeably when we're talking about distributions for one quantitative variable. A distribution that tends to be more concentrated at the center has low variability, and a distribution that tends to be more spread out horizontally has high variability. So if we look at these two examples right here, both of them represent heights. So we're talking about heights of adults in the US versus heights of professional basketball players. One difference we would expect to see is that the professional basketball players tend to be taller, right? And quite a bit taller, not just a little bit taller. So that is reflected in the fact that these numbers here at the base are generally higher than these numbers over here. Really, if anything, they appear to just be about this part of the distribution. The particular sample we have of adults in the US doesn't seem to include all of these professional basketball players. However, in addition to these basketball players being taller in general and these numbers being larger, we also see less variability in the set because we're only taking the tall people, and there's only so tall that people can get. It looks like around 80 inches here is about where we max out. So that would be 6'8", which is really quite tall. And we don't see anybody going below 72 inches, which is 6'2". And therefore we see that all adults in the US, we have more spread out. And among professional basketball players, we see heights that are more concentrated at the center. Therefore, we would say there is low variability among professional basketball players, and there is relatively high variability among all adults in the US. It doesn't really make sense to ask this question without a comparison, right? So I can't just give you one distribution and say, is the variability high or low? Because the graph can be drawn in such a way that makes it look like the variability is very high or like the variability is low when we choose the scale over which to draw it. So it only makes sense to compare two distributions if we're just asked for a general question like, is the variability high or low? A commonly used measure of variability is something we call the standard deviation. We use the letter S if we're talking about standard deviation for a sample. We use the Greek letter sigma if we are talking about standard deviation for a whole population. Note that this symbol here represents the lowercase Greek letter sigma. The uppercase sigma we've seen once before. This is the uppercase sigma showing up in the formula for standard deviation. Standard deviation is a positive number that is a measure of the spread. So in the examples we just looked at, adults in the US, we have a standard deviation of 3, and basketball players, we have a standard deviation of 1.2. So looking back at those dot plots, or thinking back to those dot plots, we said that we had low variability for basketball players, and we can see here that we have a lower number for a standard deviation of the basketball players. We had higher variability among all adults, and we can see that we have a higher number of 3 for the standard deviation of the distribution of heights of adults. So yes, these do appear to be consistent with what we already observed from looking at the dot plots. Let's calculate a few values and mark them on a graph so that we can understand the distribution a little bit better. Remember that x bar is the notation we use for the mean, and this S here is nu, that's for the standard deviation. Both of these sets that we were looking at were samples, not populations. We did not have all adults in the US in our data set, and that's why we would use X bar and S instead of mu and sigma. So what we're going to do here is use the values we're given. We're given that the mean for all adults in the US is 69 inches, and the standard deviation of heights for all adults in the US is 3. And so we're going to do a quick little calculation of X bar, which is 69, minus 2 times S, which is 3. So this is really 69 minus 6, which is 63. For the second calculation, our X bar is still 69, and we will subtract off a single standard deviation of 3 to get 66. For the middle here, we have just X bar, the mean straight up. Then we will take our mean and add the standard deviation to get 72. And finally, we take our mean of 69 and add 2 times the standard deviation. Therefore, we end up adding 6 to get 75. So let's find on our distributions the first and last values that we just calculated. That means we're going to locate 63 and 75 on that dot plot that we were just looking at. So for heights of all adults in the US, here is my 63 and here is my 75. We can see that those two values seem to be really close to the edges of the distribution, but they're not quite all the way at the min and the max. Well, the 75 does happen to fall exactly on the maximum value, but we can see that the 63 does not quite. So it looks like what we see here is that if we go 2 standard deviations below and 2 standard deviations above the mean, we get almost the whole distribution. They're not quite the min and max, but we can say that they're very close to the minimum and the maximum of the distribution. So let's see if this still holds for heights of professional basketball players. This time we have X bar equals 77 and S equals 1.2. So we're going to do 77 minus 2 times 1.2, and we're going to do 77 plus 2 times 1.2. Since 2 times 1.2 is 2.4, I'm subtracting 2.4 from 77 to get the lower bound, 74.6, and I add 2.4 to 77 to get 79.4. Now let's look at this distribution. Looks like 74.6 is again not quite all the way at the min, but very close to it, and 79.4 similarly not quite all the way at the max, but very close to it. Soon we will make a more formal statement about this interval that runs from 2 standard deviations below to 2 standard deviations above the mean, but right now we want to just establish that they're very close to the lowest and highest value, although in most cases they're not quite all the way at that value.